بسم الله الرحمن الرحيم والصلاة والسلام على أشرف المرسلين سيدنا محمد وعلى آله وصحبه أجمعين. This is the third tutorial, and it's actually a very short one, and it's simply a follow-up of tutorial number 2. What we're going to be doing here is showing you the going back to actually the choice that we made in tutorial number 2. If you remember, what we did in tutorial number 2 is that we derived the equations of motion of the two-link manipulator. It looks like the one that you see here, using the recursive Newton Euler approach. However, what we did in tutorial number 2, if we go back actually here, you'll find that when we placed the intermediate link frames, frame 1 and frame 2 here, we placed them at the center of mass, and we said that this is a choice. We can do that. We can also do it at any other point. What we're going to be doing here is actually we're going to be placing the frames of 1 and 2 at different points. We're going to be placing them at the joints of that connect the link to its pair. Okay, so we're going to be placing frame number 1 not at the center of mass here of the link of the link, but actually at the joint, connecting it to link number 0. The same also for link for frame 2. We're going to be placing at the center of mass here, but at the joint connecting it to link number 1, and so on. Frame 0 and frame E, they are exactly the same. So frame here, 0 actually here is placed at the same place, which is, but it's actually coinciding here with frame number 1. So it's just for visually to be appealing, it's just drawn away from it, but it's actually placed here in the same place as what we had earlier, while frame E is exactly the same at the tip of the rope. What you're going to see here is the main purpose of this tutorial actually is to actually practice computing the screw axis and the homogeneous transformations for this different choice of frame 1 and frame 2. But so there's something actually that will be surprising in this tutorial. Is actually we're going to be changing very, very few lines compared to what we had in tutorial number 2. And this is actually one of the great advantages of the geometric approach that we're following, is that all of the equations, they are invariant to the choice of coordinates, and thus when we change the coordinates from going from the center of mass frame to a different frame here, very few lines actually will be changing from the code perspective. What I'm going to go immediately to running the code. You'll find that actually this is the same. This is how the frames look like in the home configuration. Of course, we're gonna have the end effector home pose to be exactly the same. However, here and same also for the rotation matrices of the two links. But the only thing that will change here is actually the displacement of 1 with respect to 0, which in this case is 0 because they are close. Both they have the same origin, and here, frame number 2 is actually placed at minus L1 in the y direction. Okay, so this is the new location of the frame 2. What you're gonna see here is that all of the lines that will be changed or added will be highlighted here. Okay, so by this comment. So here, these are only the files, the lines that will change from tutorial number 3 compared to tutorial number 2. Okay, so keep track of these. So this is the first thing that we changed. So we'll just run that. The screw axis. Nothing of it changes. And recall that the screw axes are defined, they are geometric objects. So these are the screw axes, they are abstract, what you see here. And we express them in the 0 frame. And since the 0 frame did not change from tutorial 2 to 3, then actually we have the same part. Product exponential formulas, they are the same. Nothing changes here. The geometric Jacobians don't change. Body Jacobians don't change. Nothing here changed so far. Exactly the same. The inertial parameters, they are actually will change slightly a bit. And the reason is that the expression that we had earlier, which what we did here in this part, so the expressions that we derived here for the generalized inertia actually are only valid if you place the frame at the center of mass. So what we're going to be doing here is that since we have now that we have a displacement between the center of mass and the frame that we chose, then actually we also need to define the location of the center of mass. So this is the new thing that should be provided, which is you find here that we have psi of the center of mass of link 1 expressed in frame 1 that we chose. This vector in the tutorial number 2 was zeros, but here we actually have it's simply L1 divided by 2 in the x direction. So this is the expression that we have here. And we can also define using, we can actually place like an imaginary frame here at the center of mass. And then we can transform the inertia using this expression for transformation of inertias from this imaginary frame that we call CI to the frame that the I frame that we have here. Okay, so this expression that we have here is simply will take care of transforming the generalized inertia from being at the center of mass, which has this expression, to the one that has this expression, because this is how actually it will look like when we transform it to the frame, that's not at the center of mass. If you take a closer look at it, you find that the bottom right corner, they are exactly the same. They're still diagonal. The top right and the bottom left, they are not the same anymore. They are actually given by this hue symmetric. If you look at these two terms, you find that they look like this. And they are simply, capturing the fact that, so these two together, they are actually symmetric. And you see actually what they have in here is simply something like the mass multiplied by the skew symmetric form of the location of the center, of the displacement of the center of mass. You can go back to the expression, you'll find that actually. This is what we have here. The same also for the J matrix, we get some extra terms on the diagonal here, just because of this transformation. So now comparing both, you see, so this is how the inertia matrix looks when we in the center of mass frame, while this is the inertia, how it looks like in the frame 1 that's not at the center of mass. If we do exactly the same for frame 2, we find that actually we're just repeating the same part. And then we go to the recursive Newton Euler part. You see actually here, we also, the first thing we do is that we transform the screw axis from the 0 frame to the child frame. And there is actually something that's interesting here. So let's actually print, let's print this part and see what happens. If you actually, and let's also print, just let's see, let's also print here these two screw axes, which are the screw axis, but expressed in the 0 frame. And what you see here below is actually the screw axis expressed in the child frame. So let's print this part and see what happens. You see here that the screw axis of the first screw axis expressed in the 0 frame is the same as expressed in the frame 1. They are exactly the same. And the reason that even though frame 1 and frame 0, they are different. However, in the home configuration, they are different. They have different orientation. However, since the z-axis, the rotation is around the z-axis, the z-axis of both are the same, and the screw axis passes through the origin of frame 0 and frame 1, and thus, there's actually no change in the transformation. So that's why these two expressions are the same. The second screw axis, so which we're talking about this screw axis expressed in frame 2 compared to expressed in frame 0 actually will give different results because they're not the same frames, and they're also displaced from each one another. If we look at the frame here, we'll find the second screw axis expressed in the 0 frame. We can get this expression here, that we've seen earlier in tutorial number 1. However, if you look at the screw axis expressed in the frame 2, you'll find it's also 0, 0, 1 and 0, 0, 0. And this actually will always be the case. If you check here, what we did here in this tutorial is that we defined the frames, so frame 1 and frame 2, at the joint, at the joints. And since we are talking about revolute joints, so the revolute joints, they are actually going to be aligned here with the z-axis. So here it's aligned with the z-axis, here it's aligned with the z-axis. And the screw axis, so for example, this screw axis expressed in frame, with respect to frame 1 is always passing through the origin. And the screw axis of link 2 is always passing through the origin of frame 2. And if we do the same for all of the n links of the robot, we'll find that this is always the case because we chose in this format to actually place the reference frames at the joints. And thus, actually we're going to always have, okay, that this transformation will always lead to 0, 0, and 1. Okay, and this is only because we're rotating around the z-axis. If we're rotating around the different axes, you're going to find that, okay, this vector here will change, but always going to find that the next three values are always 0. Okay, and this is actually here will bring us to a very important remark that actually we could have, that's a choice we could have done, that instead of by just looking at the home configuration, instead of defining the screw axis in the 0 frame, we could have defined them in the joint frames and then transform them to the 0 frames. Okay, okay, alternative. Okay, so this is also a choice that we could have done. Okay, but this is just the procedure that we will do here. And in this case, actually, we don't need these expressions. Okay, we don't need to look at them. But it's very important just to take care of. We can use them actually as a sanity check to actually see whether actually when we wrote these expressions here, so because we inputted them here, so in this part we actually did it correct, so that provided like a sanity check. Everything else is the same, so surprisingly we don't need to change anything else. So actually, if you go back to the recursive Newton Euler approach, actually it doesn't care where you place the frame. You just follow the steps. We didn't change anything from tutorial number 2 to tutorial number 3, and thus we get exactly the same expressions. So nothing else changes. If you now, what you need to do is that you need to compare this G term to the C term and the mass matrix. Compare them to what we did in tutorial number 2. You'll find that we get exactly the same expressions, and we did not change even one line of code in the recursive Newton Euler section. Okay, so this is actually shows really the strong invariance. Is actually something called form invariance or like coordinate invariance to what we choose. And that's it. Actually, that's it for tutorial number 3. It's just simply follow up to what we did in tutorial number 2. And in this tutorial, we just place the frames at the frames of the intermediate links at the joints instead of at the center of mass. And in this last part, we just save all of the variables that we defined in this tutorial because we're going to actually need it for the next one.